Hey there, chemists. In this crash course, we're going to review what you need to know about solutions for the AP exam, breaking it down into three things. Number one, how to use molarity. Number two, what we look at for solution formation. And number three, the Beer-Lambert Law, a common lab practice that all AP chemists should be familiar with. So starting with molarity, everybody should know that molarity is just a concentration. It's moles per liter, specifically moles of solute per liters of solution. And something that might be useful is to remember that whenever you multiply molarity times volume, that's a way of getting moles. So you might be given amounts of some reactant in milliliters, and its molarity, and that actually, if you multiply it, will give you millimoles, which are just as useful, I think, but that's a common thing that you'll have to use. For solution formation, I actually want to talk a lot about this picture that I have over here to the right, which shows the concepts related to what happens when a salt dissolves in a solvent. So let's say that an AP exam told us that this was a sodium chloride crystal, and in order for this to dissolve in water, it has to break apart. You have to separate the ions themselves. That means you break ionic forces. And that's true for any solute. You break apart whatever force of attraction is keeping that solute together. Likewise, the solvent, let's say this is a bunch of water molecules, and the next picture shows like spaces to make room for the solute particles. That means we're breaking the IMFs. For example, H bonds, when we form the solution. And then when the solution actually forms, you're forming new interactions between the solute particles and the solvent molecules around it. That's called solvating. So we are forming in this solution, we form, a good term to know is ion dipole forces. That's what happens when an ionic solid surrounds itself with water molecules. So we broke things and we formed things, and what you should know is that every time you break, that's absorbing energy. And every time you form, that's releasing energy, just like for a chemical reaction. So even for physical changes like this, we can talk about the delta H of this process, the change in enthalpy. And a common question might be, how can you explain the relative strengths of the ionic and intermolecular forces of the solute and solvent compared with the ion dipole forces formed in the solution? Well, I'll tell you, for sodium chloride, it's known that when you dissolve it, it's endothermic. It actually gets colder. Salt water is colder than regular water when you first make it. And they might ask you to explain why that is, and a perfectly good answer would simply be more energy is absorbed in breaking water's IMFs and NaCl's ionic forces than what's released in forming ion dipole forces. Now, not all salts dissolve endothermically. That happens to be true for sodium chloride, but you could imagine just saying the exact opposite. If delta H was negative, that would mean it was exothermic. The solution would get warmer as it forms, and you would simply say the forces that were formed were stronger than the forces that were broken. But that concept is always true. You always break something, and then you always form something, and what we can measure is the net effect. So a lot going on in there in solution formation, but a very common concept that's asked about on the AP. The last thing to review before we look at some practice questions is what's called the Beer-Lambert Law, or Beer's Law. This is the relationship between absorbance and solution concentration. There's actually an equation on your reference table that looks like epsilon, B, and then C. A is just the absorbance of visible light, or frankly any form of light, but usually done with visible light. E is the molar absorptivity, and that is based on what the substance is. Every chemical substance has a certain amount of absorptivity that is proportional to just how much light that particular substance absorbs. B is the path length, and C is the concentration. So if we imagine having some solution of something that has a visible color, like a copper sulfate solution, we can send light through that solution, and we can actually measure how much light goes through what's called the transmittance, and indirectly turn that into how much light is absorbed, and that can tell us how concentrated the solution is. In fact, this is a linear relationship. You can plot absorbance versus molarity, and you can see a nice linear relationship, so that at different absorbances you have quantifiable molarity. And the darker the solution, if I just imagined making this more concentrated, you would have an even higher absorption of light. So we can measure an absorbance and turn it into molarity. It's one of the main ways we measure molarity in the laboratory. Just look at how dark it is quantitatively with light. There's another graph that you might see related to absorption of light. It's also an absorbance graph, but this one is a plot of absorbance versus wavelength of light. And it's just useful to know that if you see one of these curved graphs for some particular substance, it gives you the absorbance of some substance at different wavelengths of light, and all you need to know is that you're looking for the peak, the maximum absorbance. That's called the lambda max, and it's just what you set your instrument to. And if you measure the absorbance of some substance at a different wavelength that's not at the maximum absorbance, you're going to get you're going to get a lower absorbance. So that's just something to look out for. Okay, let's look at some practice questions related to these topics and see if we can apply what we just reviewed. First up, what volume of 0.1 molar HCl do we need to make 250 mils of a 0.025 molar solution? This is the dilution equation. M1 V1 equals M2 V2. Remember when they give you a volume and a molarity and you put that of in between? Those go together. So 250 mils of 0.025, I can put those for M2. So 0.025 molar and 250 mils. And then my initial molarity is 0.1. I'm looking for V1. So V1 is the product of these two divided by a tenth, which means it's really multiplied it by 10. So I'll change that 0.025 to 0.25 and then times 250. So that's like a fourth of 250. If I think about that in my head, a fourth of 250 is 62 and a half, and that's the right answer. So we're done. Notice if you keep your volume in milliliters, they're consistent. The units just have to be the same in this equation. They could frankly be cubic feet if I want to. You don't have to convert this to liters. Leave it in a bigger milliliter number to make the math easier to think about. Okay, next question. Below is an absorption curve for a red dye, and we analyze it with the same concentration, but the sample holder is covered with fingerprints. How will the curve be affected? Well, let's think about what's going on. So here's some sample that's holding some amount of a red dye. And how this works is you measure how much light is absorbed by the solution and you see what comes out. You actually observe what's called the transmittance, which is inversely related to the absorbance. And you can turn one into the other, and that tells us how much light is being absorbed. Well, if there's fingerprints all over this thing, or there's smudges, you're going to absorb more. That means we're going to think it's more concentrated. It's going to look like it's more concentrated. We're going to think it's darker. So at some given wavelength, the absorption peak should be higher. we're going to absorb a higher amount. So this should be a higher peak. So looking at the choices, the peak will be higher because more light will be absorbed. We've hit the right answer right away in choice A. Just checking, the peak will be lower. No. The peak shifts left or the peaks shift right. No, that would change the wavelength, and we're not doing that because we're still studying the same color of a solution, so we would use the same wavelength of light going into the mixture. Let's go to the next one. Suppose you want to use a spectrophotometer to analyze a solution of blue dye, but they rinse the cuvette. That's one of these square sample holders is called. That's called a cuvette. And they didn't dry it, so there's water before they dry it. How would this affect the absorbance? Well, if I have some cuvette with blue dye in it, but then I do it again where it's got water droplets in it, that's going to dilute it. It's going to be less concentrated. Less concentrated. So it's going to absorb less light. It's just going to be lighter. It might not look lighter to the eye, but these machines can tell. So how will this affect the absorbance? It should be less. It will be lower because the water droplets will dilute the solution. Once again, we've hit the right answer right away in the beginning. B says it'll be lower because it will change the optimum wavelength. No, we do that by changing what color we're studying or just what wavelength of light we actually use. So B is incorrect. And then C and D are both incorrect. They say it will be higher, and that's incorrect. Okay, last multiple choice. Consider the 4 ions. Which one would have the strongest Coulombic attraction? A Coulombic attraction is based on Coulomb's law, which is the force of attraction between charged particles is a constant times the product of their charges, Q1, Q2, divided by their radius squared. So the closer they are and the farther they are and the greater the charge magnitude, the stronger the force. So greater charge and greater, closer distance is the greatest force. Really, it's a conceptual thing. This is the equation. You'll never have to solve for anything in a chem class for the most part. You'll certainly see this in physics and have to quantify things, but for us, it's all qualitative. Greater charges, and the closer they are, which really means smaller ions, that's what that really means, then the greater the Coulombic attraction. So which one would have the greatest one? You're looking for the smallest one with the greatest charge, which must be the magnesium. So I'm just going to circle B and make sure it says a correct statement, and it does. Largest charge to size ratio. So that's it for multiple choice. Let's take a look at one two-part free response question. It says they're talking about this molecule here that they react with dichromate to make a different colored chromium compound. So we have something that's orange and it changes color. They make a solution of dichromate that's initially 10-3, and they react it with an ethanol concentration. They keep the acid pH the same. They put it in a cuvette that's specifically 0.5 centimeters and place it in a spectrophotometer with a set wavelength. And they monitor the chromate or the dichromate as a function of time by looking at absorbance. Lots of information in that paragraph, but the key information I think is in this table. As time goes on, the absorbance goes down because they're monitoring the consumption of this. This is almost something that could be a kinetics question if we wanted it to, but they're just looking at the disappearance of this reactant over time. What's the value of the dichromate at 1.5 minutes? Well, remember that absorbance is related to molarity. So I could quantify the molarity of dichromate as a function of time as well. They told me that originally it's 10⁻3. And they want to know what is it at 1.5 minutes. Well, this means I need to just remember that molarity and absorbance are directly related. So the ratio of this 10⁻3 to 0.782 should be the same as whatever my unknown is to the next one, 0.553, because it's a linear relationship. So I can set up a ratio of proportions. The unknown dichromate concentration, Cr2O7, to negative at 1.50, divided by the absorbance of 0.553 is equal to the initial 1.0 times 10 to the minus 3 divided by the initial absorbance. So I'll just dig out a quick calculator, and you can take 10 to the negative 3 times 0.553 and divided by 0.782, and looks like the molarity ends up being 0.0007. So, and that makes sense because it's less. As the absorbance decreases, the molarity should also decrease about 7.1 times 10 to the minus 4 molar. I'll just give them two sig figs because that's how many were in the initial molarity. Last question. The student runs a second trial, but they change the path length. What's the experimental setup that should be changed to keep the absorbance the same? Here we go. This is a PhET simulation that relates absorption and solution concentration that really illustrates what Beer's law looks like. And we can see we have a 100 millimolar solution with a path length of half a centimeter. And now the absorbance in the animation says it's 0.48. Let's change the path length to be a centimeter. And you can tell it as the path length increases, the absorbance increased. So to compensate for that, I'm going to have to decrease the original concentration, and it looks like I have to cut it like exactly in half to get down to the same absorbance. And that makes sense when you look at what we have, because absorbance, is that absorptivity times path length times concentration. So to keep the initial absorbance the same, we should have the initial molarity to compensate for doubling the path length. Direct application of Beer's law, somehow commenting on the fact that absorbance is directly related to both the path length and the concentration. So if I double the path length, I better cut the concentration in half so the absorbance stays the same. Same chemical substance, so the absorptivity stays the same. That coefficient goes with what chemical you're studying, in this case dichromate. So as you can tell, there's a lot of questions that come up about Beer's law, this relationship, mostly conceptual, about absorbance of light and how concentrated it is, but also how much distance is traveled. That PhET simulation is very good if you want to play around with it. Just search PhET, P-H-E-T, and Beer's law. It's done by the University of Colorado. They have a lot of great simulations for students to learn. Hopefully that was a useful crash course on solutions, and thanks for watching.